Okay, in this video, we're going to be talking about polynomial functions like x to the second, x to the third, x to the fourth powers. So linear, we've already done, y equals mx plus b, we know, and I want you to look at the patterns here. Okay, so first power, linear, we already know is a line. Second power, we know is a parabola. Now, I want to show you how this pattern exists and what happens when you go from a first, actually from a first to a third to a fifth. So when you go to a third power, instead of linear, you're going to have an extra hump somewhere in the middle. Okay, so it's going to, for the most part, it's going to look like something like that. And I'm going to skip over to a fifth power. So it's going to be the same thing, but instead of one hump, you're going to have two humps in the middle. But now look what's happening to the left side and right side. Left side and right side. They're all the same thing unless it gets flipped. Okay, go to quadratic, second power. Fourth power looks a lot like a quadratic with a little hump. If there was a sixth power, it's going to look more like that. Okay, it just have an extra hump in the middle. But what we're concerned with is what's happening to the outside. Now, what if we flip it? What if there's a negative out front? The whole thing flips down, and this is going down on the left side and the right side. What if this has a negative out front? Then it gets flipped, and it's doing this to the left side and right side. So let's graph some of these, and we're going to sketch these graphs. We're not going to actually graph them because these things take a good while, and if we're actually going to graph, most of the time we're going to use some sort of graphing technology. Okay, so for the first thing we're going to do is we're actually going to factor these things. We're going to factor. Once we find the factors, we can set them equal to 0, and we can find our x-intercepts, or what we call our zeros. Okay, first thing I notice is all of these have an x. So I'm going to factor that x out, and I'm left with x squared minus 2x minus 24. Next up, I can factor this quadratic trinomial, x and x. What adds and multiplies give me this and this would be a minus 6 and a positive 4. Set each factor equal to 0. Solve, you get x equals 0, x equals 6, and x equals negative 4. So this thing's going to cross. I'm going to go ahead and just, like I said, we're just going to sketch it. It's going to cross at negative 4, it's going to cross at 0, and it's going to cross at 6. Now an x to the third graph, notice it's a positive x to the third, is going to be like a line, except for, again, it's going to have that hump in the middle. These are the places where it crosses. So notice the pattern. This thing's going to go up, down, and then it's going to come back up again. And like I said, we're mostly interested in what the graph would look like, just a sketch of that graph. Now here we have a negative x to the third graph. So instead of up, down, up, this thing's going to flip over and actually come down, up, down. Okay? So first thing we're going to do, again, let's factor. I'm going to factor that negative 1 out. So we have negative x to the third minus 3x minus 2. So now what we've got to do is we're going to have to use some synthetic division to actually figure out what these zeros are. Okay, so I'm going to come over here, and I've cheated a little bit up here to work ahead of time so I kind of know where to go from here. So we're going to break this down. So we have 1. Notice there's no x squared term, so you do have to put a 0. Then you have a negative 3 and a negative 2. Bring it down, multiply, add, multiply, add, multiply, add. So therefore, we have, as a factor, bring the negative down. Our first factor is x minus 2. Then what we can do is take this x squared plus 2x plus 1 that we got as a remainder and go ahead and split it into x plus 1 times x plus 1. So we're going to have factors at x equals 2, x equals negative 1, and x equals negative 1. Now, something weird happened here. We have what's called multiplicity. Anytime we have a root of the same number twice, something different's going to happen there. So let me mark my points. Okay, negative 1 is going to be about right there. 2 is going to be somewhere right in there. So anytime you have an even multiplicity, and what I mean by that is notice negative 1 is going to be a root twice. What's going to happen is your graph, instead of crossing, notice how it crossed, and crossed. Instead of crossing, it's going to touch. It's not going to completely cross it, but it's going to come down, touch it, and then go back up. So again, let me remind you, negative x to the third, here's what positive x to the third looks like. Here's it flipped to negative x to the third. So this graph's going to come down. it's going to touch at -1, go back up, and then it's going to cross at 2. And the reason for that, again, is 2 is a factor once, and -1 was a factor an even number of times twice. Now, again, on this next one, I definitely cheated on it because I didn't want to go through the whole synthetic division. So what I did is I went ahead, factored this thing out before we got started. So x equals 2 is a factor. Now, instead of writing x minus 2 times x minus 2, notice what I did. I put squared. So that means x minus 2 happens twice. So that's going to have an even amount of roots there. You also have x equals -1 and x equals -4. Now, this is a fourth power. So let's go through our sequence. We have x squared, which we know what it's going to look like. And x to the fourth will be the exact same thing with an extra hump in the middle. So it's going to be more of a W shape. So let's see. Let's put us a mark at -1, which is somewhere right in there. We're just sketching. -4, which is going to be located somewhere over there. And then x equals 2, which is going to be somewhere right in there. So we know it's going to cross, cross, touch. So therefore, this thing comes down. It's going to go back up. It's going to cross at both of those. Then it's going to come back down. It's going to touch and then go back up. So our graph is going to look somewhat like that. Now, if you actually wanted to find points, exact points, and make this graph look better, such as you could plug in zeros for x's and figure out that, hey, this thing's going to cross at 16, and you could actually find some points on it, make it look better. But most of the time when we're dealing with polynomial functions, we just need to know a general shape of that graph instead.